Pascal, come on up here. He's with SETI. He's the planetary scientist in charge of the Mars project, but most recently, you did this 500-kilometer trek across the Northwest Passage on thin ice. Do you want to talk about that?
Well, other than the ice was very thin, very rough, and it's not a passage. So we were hoping to do 2,000 kilometers on the Northwest Passage to get the vehicle all the way to Devon Island. And we succeeded in doing 500 kilometers.
This was a big, heavy Hummer type thing.
It was a Humvee on tracks and escorted by snowmobiles, which were scouting on the ice as well. But the ice sheet was covered with fresh, soft snow, and so we could not see the leads in the ice. And there was a radar behind the vehicle, but not in front of it because of the interference from the engine. The EM waves from the engine running would interfere with the radar. So it was a rear-mounted radar. So we got beautiful data, but it didn't tell us that there was a lead ahead of us, and we fell through it. We were able to winch the vehicle out of the lead with a 12,000-pound winch in front of the Humvee, anchoring it on the ice itself.
Wow.
So it was a fantastic adventure. It's all captured on film. It will be released sometime next year.
Wow. I'm glad to see you still alive. In any case, as far as I understand it, Pascal and his people go out into these extreme environments because that's the best approximation of what they might find out in outer space. So why don't you carry on with your story?
Thanks.
This is Pascal Lee.
Well, thank you for the welcome. I'm very happy and humbled to be here. This is an incredible event, so thank you, Moses, and everybody who's put this together. I work at the SETI Institute, and as you know, SETI stands for Search for Extraterrestrial Intelligence. But the truth is, we are interested in the bigger picture of life, what it means, where can it possibly happen, are we alone, all of these important questions that pervade our culture and concerns, but at the same time that we tend to dismiss because somehow they are beyond our daily worries. But today I'd like to sort of revisit an item that's at the core of the SETI Institute and its mission, which is the Drake equation. The Drake equation was put together by Frank Drake when he organized a conference back in the early 60s. He wanted to organize a conference that would essentially discuss this whole issue of the possibility of finding an intelligent civilization out there. And he thought, well, we have to bring in people who know about astronomy and star formation. We have to bring in people who know about planet formation. We have to bring people who know about the origins of life. We also have to bring people who know about the survival of life. Okay? And so by putting together his conference and the different sessions, he ended up with an equation. Because the number of civilizations in our galaxy today would be a term that would depend on the factors that would come out from each and one of these sessions. Okay. So let's see where this number stands today. At least that's my opinion. But before I go into it, let's do a quick survey. How many of you actually believe that we are literally alone in this galaxy? Okay. Right. How many believe that there might be hundreds to thousands of other intelligent civilizations, meaning like ourselves or better off? Okay, that's interesting. How many of you think that actually we might be teeming with life in this galaxy and there might be tens of thousands of civilizations out there? Okay. All right. Okay, so I approached this review of the Drake equation without any presumption of what the answer would be. Okay, and so here's what I found. Next slide. Oops, that's under my control. Could we maybe dim the lights? Thank you. So the question is, what are we? Not so much, not even who are we, but really what are we? Are we, from a physical phenomenon standpoint, are we a unique feature in the universe, or are we something that somehow has occurred commonly? It might have taken different forms, but here we are. And should we consider ourselves to be somehow, the fruit of divine intervention and intent, or are we something that might be just a matter of course? given the opportunity. In any case, all of our concerns have resided mostly on this planet. Okay, our thoughts might be erring away from them, but all the things that we worry about, including sea level rise, are all about this ball. Meanwhile, we're traveling around the sun at about 30 kilometers per second. Okay, so we're careening around the sun at that speed. The sun itself is making its way around the center of the galaxy at about 200 to 250 kilometers per second. Okay, and it takes us about 200 million years to go one full round around our galaxy. Okay. So this is the Drake equation. All right, it tells you. And it's more like a formula. It's not really an equation, it's a formula. And the number n is the number of intelligent civilizations in our galaxy. So what is this number? Well, it's going to be the product. All of these are just terms that you multiply to one another. And it's the rate of star formation times the fraction of stars that have a planetary system. The assumption being there that not necessarily every star will end up with a planetary system. And then among those planetary systems that do form, what's the average number of planets within that system that might be suitable for life? And we're quite geocentric about that definition. Suitable for life means that there's liquid water, because that's what we like. There's, of course, nutrients, and there's a source of energy. And not only is water present, but it's water that's present for quite a while. Then, among those planets, what fraction of these planets that are suitable for life, on which there's water, on which life actually appears? Okay. So therefore, not every planet that has water, we're saying, would necessarily evolve life. Only a fraction of them, and that's the factor F sub L. And then among the planets on which life does appear, what fraction of these planets will see intelligent life emerge? Now, that's a matter of definition, but it's not really a problem for this equation because you can set the bar of intelligence pretty much wherever you want. We're just saying that, let's say, something like human beings appearing is what we will consider intelligence. Okay. Beyond that, once intelligent appears, how many of those planets with intelligent life might actually see an intelligent civilization emerge? Okay. And now we're getting a lot more specific about what we mean by definition an intelligent civilization. We're talking about a civilization that's capable of radio communication. Okay? So somebody has come up with Maxwell's equations, okay, in that civilization and is understanding the propagation of electromagnetic waves, can put together a radio telescope and start beaming news about him or herself out into the universe. So that's what defines an intelligent civilization. So by this definition, we've been intelligent ever since we've been broadcasting, essentially, or emitting the electromagnetic radiation in a significant way into space, so since maybe the 1920s or so. So about a century we've been intelligent as a civilization. And then finally, what determines this number is what's the average length of time that a civilization will survive. Okay? And obviously, as soon as a civilization emerges, it's able to survive a long time. If this number L is large, you can see that we will have a chance to overlap in time in the universe, in the galaxy. Okay? If, on the other hand, L, the average lifespan of a civilization, is short, we might be like Christmas tree lights, coming on and off, but at different times, we will never quite be able to see each other. So what's our substar? Well, this is a planet-forming region in the galaxy, and we now know from my colleagues at the SETI Institute that the rate of star formation in our galaxy is approximately 20 to 50 stars a year. That's actually a pretty well-known number, give or take. And in our estimate here, I'm going to be conservative. I'll take the lower number. Roughly 20 stars a year is forming in our galaxy. What fraction of these stars have planetary systems? Well, we have become increasingly aware of these gas clouds of gas and dust called nebulae. Many are seen to actually collapse into disks, which are a key phase in the formation of a planetary system as we understand them. And we also have been discovering more and more, both at the SETI Institute and outside, of course, of the Institute, extrasolar planets, meaning planetary systems around other stars. So at the very top, you have the Sun with Mercury, Venus, Earth, and Mars to scale. Okay? And then these are just a selection of stars around which planets were found in recent times. The color coding just gives you a sense of the size of the planets that were found around them. So more and more we're finding around nearby stars, because of the ones that we can see the best, planetary systems around them. So roughly, the estimate currently is that the fraction of stars that have planetary systems around them is 5 to 20%. Okay? And if we are conservative, but at the same time a bit optimistic, we'll take the middle ground here, and so F sub p might be 0.1, 10%. What about the number of planets within a planetary system that might have an environment that's suitable for life? So, first of all, we should define what we might call a habitable zone here in a planetary system. It's a space around your star in which, on a planet, you might find environments in which liquid water is stable for long periods of time. And so in our solar system, the habitable zone is, by this definition, ranging from somewhere just within the Earth's orbit all the way to Mars's orbit. You notice that Venus and Mercury are today not in the habitable zone of the solar system. And beyond Mars, you're dealing mostly with icy bodies, unless there's somehow a source of internal heat to compensate for the distance from the star. The habitable zone would be smaller, of course, around smaller stars that are, creating less warmth around them. So this is why Mars is such an intriguing object for us. It's not just because it's near us, it's the fact that in this whole picture of looking for habitable planets, it's the one that holds the greatest promise of having liquid water on its surface. Over the years, our exploration of Mars has been telling us some important things. There was liquid water flowing early in the history of Mars. This is a picture of the Martian highlands. Okay, the southern hemisphere of Mars is very heavily cratered. It's been therefore exposed like an old wrinkled skin. Okay, it's been exposed to the elements for a long, long time, including the bombardment of asteroids and comets. And you can see that this terrain also bears the scars of water erosion. I mean, that's the most likely fluid that carved out these valley networks. In the middle history of Mars, there's also evidence that liquid water, at least every now and then, was able to flow onto the surface of Mars. So we see liquid water early in the history of Mars, liquid water in the middle history of Mars, and liquid water in recent times on Mars. These are very finely chiseled gully networks that you see on the flanks of, or on the walls of canyons or on the walls of impact craters. And we know that they're not very ancient because they're so delicately chiseled into the landscape they would have been covered by dust, sand, or obliterated by later impacts. Okay? None of that has happened, and so we figure that these gully systems are no more than about 100 million years old. Okay? So they are, geologically speaking, very young. And so this has been a very important realization from all these orbital missions, and that is that liquid water has somehow been able to affect or be present at the Martian surface both early in the Martian history, throughout the middle of Martian history, and in recent times. What the recent rovers have revealed to us that's most relevant to this whole issue is that liquid water has been present near the surface for long durations, continuously. Okay? What you see here at the bottom of this outcrop, which is part of the wall of an impact crater, are beds of ancient sand dunes. But they're all cemented together today. And in fact, if you look between the beds, you will find these famous blueberries that have been reported in the science literature. These blueberries are minerals that were concretioned by the fact that these dunes were soaking in liquid water for a long, long time. Okay? And so salts were exchanged, minerals were transformed, and concretions were formed. And in fact, the deeper you go down this column of solidified sand dunes, okay, petrified sand dunes, the larger the size of the blueberries, indicating that the longer these layers were permeated with water. Okay? And so now we have not just snapshots of liquid water being present on the surface of Mars, throughout Martian history, but we have evidence that liquid water was ponding for substantial amounts of times very near the surface, even in equatorial regions. So that actually is really exciting because even though there's no liquid water that's very obvious at all, in fact there's none that's obvious at all at the surface of Mars today, there's evidence that this has been a watery planet and therefore it might be habitable, including today, for things that are happy enough to be on Mars, such as microbes. The other thing that we need to do is to broaden this definition of habitable zone to not being just dependent on distance from the sun. You might have environments within a planet that could be warm enough where you might have liquid water. So that could be the interior of Europa, one of the moons of Jupiter, or it could be the atmosphere itself of Jupiter as well. So to remain conservative, in our solar system, we might be able to count up to 6 planets that you might qualify as habitable, in which liquid water seems to be a relatively common occurrence. And meanwhile, just to remain conservative, let's call n sub e to be about 1. What about the fraction of these planets on which life actually appears? Well, back in the 50s, Stanley Miller and his advisor, Harold Urey, made this very important first experiment, which was to zap a number of organic gases, methane, ammonia, water, hydrogen, in a simulated atmosphere with lightning discharges. And what they were able to recover in a very short time were amino acids. Okay? And so that was extremely good news. But since then, we've been able to go a bit further. Our efforts in labs have managed to create proteins and things that look like RNA material, but so far we haven't been able to really go beyond that point. And it's been very, very difficult. There's some sort of a wall of complexification of the organic chemistry that you can somehow create in a laboratory environment. So what's preventing life from appearing in a test tube is sort of the question that we are up against. And the answer that I'm comfortable with, but is still being wondered about, is it might be simply a matter of insufficient opportunity, insufficient time, insufficient mass. Okay? In a test tube, you only have so many chances of interacting with another product you want to combine with, whereas in an ocean and with geologic timescales, you might have more chance. In any case, on the Earth, the fossil record indicates, and Canada is a fantastic place for this because of all the Archean rocks that we have in Canada. The geologic record tells us that life appeared on Earth as soon as there was liquid water. Okay? In all the earliest sedimentary rocks that are pointing to a water-rich surface on the Earth, we find things that are convincingly fossil-like. Okay? And so the sense is that microbial life was able to gain a foothold on the Earth almost as soon as liquid water was abundantly available. Okay? This step between the Earth forming and microbial, relatively simple life appearing seemed to be almost automatic. And so the big question about our search for life on Mars has to do with this. Okay? Was liquid water there long enough for microbial life to also have appeared on Mars? Okay? And is this a place actually where there are fossils to be found? And of course, at this stage, we do not know what the answer to this question is. But to me, this is sort of the big question mark about Mars. This is what makes this planet stand aside from all the others. It's this beautiful and fundamental question that has yet to be answered. So the fraction of planets on which life actually appears, because it has appeared so quickly on the Earth, as soon as the Earth was habitable, it was inhabited by microbes. Let's be optimistic here, and let's say that life automatically appears. Okay? And what we're saying here is that if you have a planet on which there's liquid water throughout its history, if it's habitable for this amount of time, if it can have this branding of habitability, then life in microbial form will show up. What about going from there to intelligent life, something like human beings? Well, this is a quick summary of life on Earth in the last 600 million years of the Earth's history. So it's only a fraction of the Earth's history. You can see that fish were followed by plants, amphibians, reptiles, dinosaurs. Humans are a late comer in this whole process, and anything that might be called a human did not show up until 2 to 3 million years ago in the fossil record. Okay? This, in turn, is only a very small fraction of the total duration of Earth history. This is actually at the very top there. What we just saw, the latest 600 million years are compressed at the very top. This is the entire length of Earth's history. Okay, so Earth was put together 4.6 billion years ago. The oldest rocks known are about 4 billion years in age. We can see that there are fossils as soon as there's a record of rocks. And so that's telling us something, I think, that's important about how easy it seemed to have been for microbial life to appear. But meanwhile, something that we would qualify as intelligent like ourselves, okay, that's something that only happened at the very last minute. In fact, it took billions of years to happen. Okay? And so while life might be something that you could believe is straightforward, intelligent life is something that could be very difficult to achieve. And on the Earth, certainly, it took about 1,000 times longer, all right, than it took microbial life to appear. And this actually could be a number that's much smaller than what we even have here. But let's say that the fraction of planets on which life has appeared and on which intelligent life evolves is about 1 in 1,000. Okay. I'll skip through this. There are circumstances that have made the Earth able to support life over such long timescales, but I'm going to skip over this. Finally, the fraction of those planets with intelligent life that see a civilization emerge. Well, this is the definition of a civilization, okay? It's golden eye. We want to be able to communicate with the rest of the universe. And if you look at how quickly we went from, geologically that is, from appearing as humans to being able to communicate, essentially you might be led to believe, for the same reason as you did perhaps for the emergence of microbial life, that an intelligent civilization is something that follows relatively readily as soon as intelligent life appears. And so therefore, the fraction of those planets that have a civilization emerge out of just intelligence is about 1. Okay. Finally, what's this factor L? Okay, so the longevity of a civilization, well, we know now and understand better that we are subject to giant impacts. There are other natural causes that could be global catastrophes for us, overpopulation, pandemics. This is beautiful Houghton Crater, which I've spent 12 summers of my life working on Devon Island in your beautiful Canadian Arctic. It's a fantastic site. It looks like Mars in many regards, but it's just a typical example of a cosmic impact scar. We're also susceptible to world wars, and so as optimistic as one might be, the only fact that we really have to hang our opinion on right now is that we have survived as a civilization, as an intelligent civilization, for maybe a few decades in our case, for about 100 years, but let's be optimistic and call it 500 years. Okay. So what does n end up being? Well, if you're very optimistic, you might end up with n equals 50,000. Okay. If you just somehow think that everything is inevitable. If you're pessimistic, and in particular with some really low numbers for f sub L, you end up with a number that's much smaller than 1. And that is actually in contradiction with reality because we do exist. Okay. Then you do have our discussion here in the numbers we favored. And with the numbers we favor, this is the answer. Okay. And the message is this. I don't necessarily believe in this, and it's not a matter of believing in this number. The point here is to realize that we might well be alone in our galaxy. Okay, this is a distinct possibility, even if life is a natural process and the emergence of intelligence happens whenever it can. And so this particular solution actually is consistent with what we observe. We haven't seen or been able to hear anything so far to establish contact. It's consistent a bit with the Fermi paradox. The Fermi paradox was, if there are civilizations out there and so many of them, why haven't we heard from them yet? Why haven't they come here? Okay. And if the numbers n equal 1, well, that's why. Okay. So even if n was 100, okay, with a galaxy that's 100,000 light years across, the ballpark average distance between each civilization would be about 1,000 light years. Okay. And so even if you're off in this estimate by 2 orders of magnitude, we are, for many practical reasons, very much alone. Okay, thank you.
Thanks, Pascal. That was